thank you to Skillshare for supporting this episode of Journey to the Microcosmos. And if you're one of the first 1,000 people to click the link in the description, you can get a 2-month free trial of Skillshare's premium membership. When you go for a walk and you feel perhaps the soft squish of nature underneath your feet, you are in fact walking along the home of plants and fungi and microbes. The soil itself might just seem like dirt, common, ubiquitous, mundane. But dirt is essential. It is where everything you eat comes from. It recycles wastes, it cleans water, it makes your life better in millions of tiny ways you never notice. And also, it is mysterious, housing a complex network of reactions between plants and microbes. We can't see it with our eyes, but it's like an economy built on chemical signals and nutrients and competition that take place in the microcosmos, but that shape the macro world as well. Now, microbes require water to thrive, which can be challenging in soil. On this channel, we've seen many examples of the protective cysts that many microbes form when the habitat around them dries out, like these ciliates that will remain in this state until the conditions become right for them to emerge again. But protective cysts are only a small part of the story. Soil is itself a mix of organic material, minerals, water, and air. And that fraction of water doesn't just sustain the plant life we see above ground, it provides a home to many, many microorganisms that remain hidden below. Soil is also not some mound of dirt that would be uniform but for the interruption of animals and plant roots. That world underneath our feet is made up of layers and zones. For example, there's bulk soil, the area that is untouched by plant roots. Bulk soil is home to microbes. But at the turn of the 20th century, a German scientist named Lorenz Hiltner noticed that the closer the soil was to a plant's root, the higher bacterial activity he would observe. And from his work, he defined not just a new term, but a whole new world, the world of the rhizosphere. When Hiltner defined the rhizosphere in 1904, he described it as the area of the soil that most immediately surrounded a plant root. But in time, this definition has been expanded to describe not just the soil around the roots, but also the parts of the root that get overtaken by microbes. But the rhizosphere isn't just a location. It's a whole set of interactions between plants and microbes, and with the complex ecological relationship that builds, the soil of the rhizosphere can actually look quite different from bulk soil, from the types of nutrients to its pH. But different plants have different needs, and so the rhizosphere is a dynamic and varied thing that changes according to the microbial communities that inhabit it and the complicated chemical language they share. In the big picture, roots provide structure to plants, but they also play an important role in the rhizosphere, sending out chemical signals that attract microbes. These chemicals can include everything from free oxygen to water to enzymes to mucilage to proteins to all sorts of other things. Collectively, these compounds are known as the root exudate, and they might be part of a plant's waste that gets excreted through the root and into the surroundings, or they might be released either actively or passively from root cells. Very broadly, the role of root exudate is to attract microbes. In some terms, you could consider it an invitation, but it's an invitation that comes with a cost for the plant. Some of those exudates are nutrients the plant themselves could use, so why spend them on an invitation? What can the microbes bring in exchange? Well, for one, microbes help plants access nutrients they might have trouble getting on their own. Above ground, plants can access carbon dioxide, water, oxygen, and light. And below ground, they get structure and many of the additional mineral elements they need to survive. But some elements, like nitrogen, are pretty difficult for plants to get. Nitrogen is essential for life, and it is also plentiful. But it is so difficult to convert nitrogen into the forms life needs, and plants aren't able to do that. Instead, they rely on the bacteria of the rhizosphere to take nitrogen and convert it into ammonia and other compounds that they can actually use. Some plants, like legumes, even form nodules on their roots to house those bacteria, creating an even tighter symbiotic relationship. Now, whenever you invite someone over, there's a little bit of a risk to that, especially when, sometimes people misunderstand the nature of the invitation. Releasing compounds that attract bacteria is all well and good until the pathogens also catch wind of what's going on. Sometimes these pathogens make it to the plant and are able to infect it, but then other times the non-pathogenic bacteria can shield the plant, creating protective biofilms or releasing toxic compounds that target the pathogens, like your good friends that help you kick that guy out who I don't think you even invited. But collecting such an active bacterial community is also a great way to attract predators. Protozoa and nematodes alike can be found in the rhizosphere thanks to the buffet of bacteria that await them. And yet this is a risk that plays somewhat into the plant's interests as well. As these predators graze on the bacteria, they excrete nitrogenous waste that can continue to contribute to plant growth. Or, in some cases, the predator dies, and they become the source of nutrients. The composition of these microbial communities is shaped by the compounds released by the plant's roots. Scientists are studying the ways these specific molecules in the root exudate can influence the presence of specific bacteria and fungi. As we learn more about the rhizosphere, we may come to understand not only how these root exudates influence the ecology of microbes and plants alike, but how we can better interact with it when growing our own crops. These chemical signals and the interactions they shape form a dialogue between different parts of the living world. They speak a language whose basic vocabulary we may understand, but whose full syntax is complex and wonderful and mysterious. Thank you for coming on this journey with us as we explore the unseen world that surrounds us. If our pretty images have inspired you to create some pretty images of your own and you'd like some help with that, you can head on over to Skillshare, where there are classes like Botanical Illustration Intensive, Draw Plants Using Science and Style. Artist and naturalist Maggie Harity will teach you to create science-based botanical illustrations of the plants you can find around you. Skillshare is an online learning community that offers membership with meaning. With so much to explore, real projects to create, and the support of fellow creatives, Skillshare empowers you to accomplish real growth. And it makes it easy with short classes that will fit into your daily routine. A premium membership will give you unlimited access, so you can join the classes and communities that are just right for you. And an annual subscription to Skillshare is less than $10 a month. And if you're one of the first 1,000 people to click the link in the description, you can get a 2-month free trial of Skillshare's premium membership. Journey to the Microcosmos is only possible because of the support of our patrons. So thank you so much to our Patreon community. These people are the reason this and all of our other episodes exist. So if you liked it, say thanks to them. You can find out more about becoming a patron at patreon.com/journeytomicro. If you want to see more from our master of microscopes, James Weiss, you can check out Jam and Germs on Instagram, where he is always posting beautiful and fascinating things. And if you want to see more from us, there's always a subscribe button somewhere nearby.